Okay, so let's begin. So it's my great pleasure to introduce Damir Dzhafarov from University of Connecticut, Stores. That's his first talk at MOPA, and I hope not the last. And he'll see what he's going to.
Okay, so thanks so much, everyone, and thanks for the invitation, and thanks everyone for being here. So yeah, it's really nice to be able to talk here. I spoke, I guess maybe it's been a couple of years at this JAF meeting, and that's also really nice. So it's nice to interact with this community. I think there's a lot of common research interests. So the title here is Reverse Math and the Game-Theoretic Framework, but yes, I guess the title I submitted was different, and it was something like reductions, games, and compactness, and all of these things will feature. So I'm sorry for changing it.
And probability.
Provability.
Yep.
Yes. So there will be something about provability in this. Otherwise, I think it would be less interesting. So so I apologize for the change to the title, but it's only to the title. So oops. So everything here will be from some work with Dennis Hirschfeld and Sarah Reitzes that was finished about last summer, and actually has been continuing in some guises since then. In particular, Sarah Reitzes in her thesis has been continuing some of this work. So so there is quite a lot of going on here, and I think and I'll try to give you sort of a snapshot of survey and a snapshot of some of the results. So because this is I think a varied audience, let me give a bit of background to start. This is sort of what reverse math is in one slide, or at least what classical reverse math, what I call classical reverse math in one slide, right? So this is the program of calibrating, well, the computability theoretic and proof theoretic content of mathematical problems, principles or problems. So we use on the sort of the proof theoretic side, we use subsystems of second order arithmetic, Z2, against as sort of benchmarks against which we measure the strength of various theorems, right? So these subsystems are RCA naught, WKL naught, ACA naught, which I think are familiar systems, but it's a second order and it's a first order. These are all first order theories in a sort of a two-sorted language, right? So we can simulate second order logic in that sense. RCA naught, which is the kind of base system that I'll be using, consists of just the kind of the ordered semi-ring axioms about the natural numbers. So the algebraic facts about the natural numbers, plus comprehension for delta 0, 1 formulas and induction for sigma 0, 1 formulas. So a very relatively weak fragment. So it's just the kind of, its first order fragment is just sigma 0, 1 induction. And then the other systems I'll mention as I need them. I won't really be going into really using these subsystems or anything. But I do want to say what models in this system are. So a model here, right, is a pair NS. N is some kind of first order structure that could be non-standard, and S is a collection of subsets of this structure. So and a model of if it happens to be an RCA model of RCA naught, then the set S of subsets of the first order structure has to be closed under delta 0, 1 definability. And omega models are just models that happen to have standard first order parts. So the first order part N is equal to omega, the actual standard natural numbers. In this case, if S is a model of RC naught, then S is what we call a Turing ideal. So it's a structure, it's a collection of subsets of the natural numbers that are closed under Turing reducibility and join. So it's a nicely behaved collection of sets. When we're sort of mixing reverse math, which is ostensibly some kind of proof theoretic framework, right, with computability, then the interface comes from thinking of mathematical statements as problems. I've already said that word, problems, right? So if you think of a sort of typical statement that one looks in this framework, it has this form. For every x satisfying some formula phi or property phi, there is a y satisfying some property psi together with x. Right, so this is a ubiquitous class of mathematical statements, has this shape. And so you can think, well, x and y are subsets of the natural numbers, phi and psi are some kind of properties, maybe arithmetical formulas. And we think of these as problems, right? We think of such a statement as a problem: given x satisfying phi, find a y satisfying psi. We call the x's satisfying phi the instances of the problem, and then we call the y, for a given x that is an instance, we call the y satisfying psi xy the solutions to x for this problem, right? Right, and so in the computability theoretic setting, as I said, we look at x's and y's that range over the natural numbers. Phi and psi are some kind of properties, maybe arithmetical properties, not necessarily, but often arithmetical. And the basic question then in computability, right, is given an instance of a problem, how complex are the solutions? So how relative to the instances, how complex are the solutions? And we can measure complexity in a variety of ways. So on the computability theoretic side, right, we can ask basic questions like, does every instance compute a solution to itself? So is the problem sort of trivial from a computability theoretic standpoint? Does every instance have, maybe it doesn't have computable solutions, but maybe every instance has a solution that's arithmetically definable relative to itself? These sort of give us upper bounds on the complexity, but conversely, we could talk about lower bounds, where we could say, is there a computable instance, all of whose solutions compute the halting set, 0 prime? So that would say that there's a computationally simple instance with computationally difficult solutions, right? So somehow this problem is computationally non-trivial in that case. And in fact, it amounts to solving the halting problem at least, right? That's kind of the way to think about it. On the reverse math side, which again, right, I mean, I'm using proof theory here in a very my sort of sense of proof theory way. We can ask questions like, is the theorem provable in RC, not in this base system? So is it as simple as it gets relative to these benchmarks? Or is the theorem provable in one of the higher systems like AC not? Or maybe we could ask, over the base system RC not, does the theorem imply AC not? Does it have some non-trivial proof theoretic component, right? And there's a well understood sort of back and forth between these two approaches. So the computability theory and the reverse math, modulo induction issues, which do complicate matters, right? There's a kind of straightforward way of translating results from the one framework to the other. So this is why computability theorists can play being proof theorists to some extent, or at least some kind of proof theorists through this relationship. There's other ways to compare problems, and this is why I sort of drew this distinction of classical reverse math. That I think of reverse math nowadays as sort of encompassing all of this stuff, including the computability theoretic perspective, and also some of these finer measures of strength that I want to talk about. So suppose we have these kinds of problems, P and Q, these instance solution pairs, right? That I talked about. Then if P and Q are problems, we can say P is computably reducible to Q if you give me an instance X of P, it computes, so this is Turing reducibility here, it computes an instance Y of Q such that from every solution Y hat to that Q instance Y, I can compute a solution X hat to X, right? So if you sort of visualize it like this, start with an instance of P, compute from it an instance of Q. From any solution to that, as an instance of Q, you can compute an instance, a solution to the original instance, right? So you can sort of computably transform or effectively transform solving the one problem into solving the other. This is a very natural reduction that's sort of often used in studying these kinds of problems. I mean, frequently when we actually prove that there's some kind of implication holds over RC not, it's actually this that we actually end up showing, right? And then we just sort of formalize and make sure that the induction isn't a problem.
Is there a typo here on this picture?
Because
I see two Y's.
Yes, I see that Y in the lower left-hand corner should be an X hat.
This should be an X hat. I'm very sorry. Yes, and chances are that's going to happen on the next slide too. Sorry about that. This should be an X hat. Thank you. Yeah. So this is like the Q side, and this is the P side. I'm sorry, that is confusing. Yeah, so this should be an X hat, sorry. Last.
No.
Okay, so yeah, and there is the issue here, but I'll talk around it now that I'm aware of it. So the uniform version of this is called Weierach reducibility. So this is something that's used a lot in computable analysis. So again, let's say we have problems P and Q. P is Weierach reducible to Q if there are fixed Turing functionals phi and psi, such that given an instance x of P, phi of x, so this should now be phi of x, sorry, is an instance of Q. And if you give me a solution y hat, any solution y hat to that instance phi of x of Q, psi, the functional psi, transforms it to a solution y to x, right? So the same exact thing, again, we can computably transform kind of the problem P into the problem Q, but now the process by which this transformation happens is uniform. It doesn't depend on the instances, it doesn't depend on the solutions. Whereas computable reducibility in principle could, right? You could say something like, well, if your instance is this, do this. If your instance is that, do this, right? If the solution to the transformed instance looks like this, do something else, right? These kinds of non-uniformities could in principle show up there. Here they can't. Here everything has to be completely uniform. So this was developed, just to give a little history, this was developed by Weierach in the 90s and then subsequently kind of explored by his students, most notably Vasco Bradka and his whole kind of team of collaborators. But it was Gherardi and Marconi and then Bradka and Marconi in sometime around 10 years ago who kind of realized that there is a way here to think of this in the spirit of reverse mathematics as a way of measuring the kind of complexity of problems. And independently, then many years later, just through sheer ignorance, in this paper with Francois Doré, Jeff Hurst, Joe Maletti, and Paul Schaefer, we rediscovered this notion and kind of made the same claim, right? And since then, there's been this kind of merging of these two communities, and it's been quite productive. And it really is a nice way to study a lot of these same problems that previously we only studied using either kind of classical computability theory or classical reverse math. Now we have these kind of more direct methods of comparing problems. Okay, so just to say a little bit more about how these things relate to each other. So if P is Weierach reducible to Q, then P is computably reducible to Q. So Weierach reducibility is a stronger notion. And if P and Q are problems that come from pi12 statements, these for all x exists y that I had on that previous slide, then computable reducibility implies implication over omega models. So if P is computably reducible to Q, then Q implies P in omega models. Every omega model of Q is a model of P. So here's an example that, I mean, it's an example, but it'll also figure in the rest of the talk. So this is Ramsey's theorem for K colorings of N tuples. So if you have, right, so how do you think of this as a problem? So RTNK has instances that are colorings of the N tuples using K colors. And given an instance, any such instance, the solutions to this are all the infinite homogeneous sets. So these are all the infinite sets so that C is constant on the N tuples from those sets. Okay, now it's easy to see that in RCA naught, the number of colors really doesn't matter, right? So if you fix the number of colors, so you have RT and J here, which is Ramsey's theorem for coloring N tuples and with J many colors, and Ramsey's theorem for coloring N tuples with K many colors. Those are equivalent theorems over this base system that we use in reverse math. On the other hand, from the point of view of these finer reducibilities, that's not the case. So with Doré, Hurst, Maletti, and Schaefer, we showed that if you have a larger number of colors, then Ramsey's theorem for singletons and that larger number of colors is not Weierach reducible to Ramsey's theorem for singletons and a smaller number of colors. These are computably equivalent because they are sort of computably true principles. But then Ludovic Petzet more recently showed that there is an analog of that does hold for higher exponents. In fact, Ramsey's theorem for N tuples and K colors, if K is bigger than J, is not even computably reducible to Ramsey's theorem for N tuples and J many colors. So there's a way to tease out, using these reducibilities, the fact that one principle is using more colors than the other one is, right? With the kind of purely syntactic proof theoretic approach cannot tell those apart. these reducibilities can. Okay. So now, as sort of the ideas of hierarch analysis and computable reducibility were sort of being merged into the framework of reverse math, Hirschfeld and Djakosch developed this kind of game theoretic approach that very nicely unifies all these different perspectives. And this will be these kinds of games that I'm calling Hirschfeld-Djakosch games, even though only this one here so far is the one that was in their paper. They all have the same flavor. This will be the kind of the core topic of this talk. So suppose we have P and Q that are problems, and let's think throughout the whole talk that these are problems that come from pi1, 2 statements, as in my slide. There are other kinds of problems that do not come from such statements, but let's here only restrict attention to ones that do. So the game Q implies P is the following. So this is a 2-player game. Player 1, player 2. They alternate turns on each move. Player 1 begins by playing an instance x0 of P. Okay. Or you can alternatively think of this as P as being reduced to Q according to this game, right? So player 1 plays an instance of P. What does player 2 do? How does player 2 respond? Player 2 plays something computable from x0, y1. And that y1 has to be either a solution to this, or it has to be an instance of Q, the problem to which P is being reduced. That's move 1. What does player 1 then do on its second move? It has to play, so if player 2 played a solution to x0, the game is over. If not, then player 2 played an instance of Q. Player 1 has to solve it. So player 1 plays a solution, x1 to y1. So player 1 played an instance of P, player 2 played an instance of Q computable from it. Player 1 plays a solution to that instance of Q. It doesn't have to be computable from anything, it can come from anywhere. It can have arbitrary complexity. What does player 2 do? It plays a set computable now from the run of the game. So player 1's original instance, x0, not selecting for me, sorry. The original x0 and this x1, which was a solution played by player 1. Okay. I mean, we could also insert y1 in there, but y1's computable from x0, so it doesn't give any additional computational power to this join. Right. So this is the only x0 and x1 are the only things that have any power. So again, what is y2? It's either a solution to this original instance played by player 1, or it's another instance of Q. And this is the game. This continues. Right. So each time player 2 plays either something that solves the original instance played by player 1, or a new instance of problem Q. And player 1's player 1 is required to solve it. Player 2 is required to play computably in player 1's moves. Player 1 has no restrictions. Player 1 can play its instances and solutions wherever it wants. So player 2 wins this game if it ever plays a solution to x0. So if it ever solves that original instance, or if player 1 maybe runs out of the, if player 2 maybe plays a really complicated instance of Q that player 1 can't solve, we'll also say that player 2 has won. In other words, if this game is finite, if this game terminates at some point, player 2 has solved the original instance, or player 1 has run out of moves. If the game is infinite, so neither of these things happens, then player 1 wins. Okay, and when either one of them wins, the game stops. Although player 1 only wins if the game goes on forever. So this is a determined game, and one of the two players wins, and one of the two actually has a winning strategy. What Hirschfeld and Djakosch showed is that this really nicely characterizes omega model implications. So if P and Q are problems, then the following is true. This is shown by Hirschfeld and Djakosch. If every omega model of RCA naught plus Q is also a model of P, then player 2 always has a winning strategy in the game Q implies P. If not every omega model of RCA naught plus Q is a model of P, if Q does not imply P over omega models, then actually player 1 has a winning strategy in this game. And I won't give a proof of this, but I'll give a proof of a related result, or kind of generalization on this. Now, remember that Weierach reducibility implies computable reducibility implies application over omega models. So there is a version of this that's sort of close also to the Weierach side of things. Well, maybe I should say before we do this, the Hirschfeld-Jacques game does capture this intermediate reduction, computable reducibility, right? Because P is computably reducible to Q if and only if player 2 has a winning strategy for the game that wins in exactly 2 moves, right? If we go back to this slide, that's exactly what computable reducibility was. Player 1 plays an instance, X naught. Player 2 plays an instance of its problem, computable from that. Player 1 plays a solution to it. Player 2 plays a solution to the original P instance, computable from that. Right, so this is exactly the diagram that I drew on the previous slide, and we can also, using this a small variation on this, capture Weierach reducibility. But for this, we need to introduce the idea of computable strategies. So strategy for player 2 is computable just if there's a computable a Turing function that tells it what to play on its next move, right? So player 2 always has to play computably in the run of the game up to this point. And so we're saying there's a functional phi that tells player 2 what to play, right? So given all the moves up to this point, phi takes those as oracle and outputs player 2's next move. That's a computable strategy for player 2. And now P is Weierach reducible to Q if and only if player 2 has a computable winning strategy. Computable winning strategy for the game, Q implies P that wins in exactly 2 moves. So again, we can capture both all of these reducibilities using these Hirschfeld-Jacques games. So their framework really nicely kind of unifies all of these different perspectives, right? Okay, so this was done maybe 5-6 years ago, and it's instructive to look at a couple of examples here, in particular this one, again going back to Ramsey's theorem. So let's look at right, I already talked about Ramsey's theorem for different numbers of colors. Let's look at just this basic one of RT12 implies RT1 less than infinity. So RT1 less than infinity is just the principle for all k, RT1k. So its instance can be a k coloring of the integers with finitely many colors, but you're not told which k. Doesn't use 2 colors, doesn't use 3 colors necessarily, just k for some k. I mean, it can, so the instances of RT1 less than infinity are all finite colorings of the integers. Whereas the instances of RT12 are just the 2 colorings, the ones that use 2 colors. Okay, so how does player 2 win this game? So player 1 plays an instance, let's say of RT1 less than infinity. And for simplicity, I'm just saying it's a 3 color. So it uses 3 colors. What does player 2 do? Player 2 plays this kind of squashing coloring, right? So it plays it has to play an instance of RT12, what it does is what player 2's, this should be D1, I'm really sorry. What it does is it says, okay, if player 1's coloring colors something 0, I'll color it 0, and otherwise I'll color it 1. Right, so it collapses the colors 1 and 2 into 1 color. Okay, how does player 1 respond to that? Player 1 plays an infinite homogeneous set H1 for this coloring D1. Okay. What does player 2 do? Player 2 defines a new coloring now operating on this set. Now, what does this homogeneous set for D1 satisfy? It's homogeneous for D1. If D1 has color 0 on this set, then so does C. So it's homogeneous for the coloring C. If it's homogeneous for color 1, then this coloring C can use 2 different colors on it, 1 or 2, because those were collapsed into 1 color. However, right, it can no longer use at least 1 color. At least 1 color is now avoided by C, right? So it's reduced the number of colorings that C can use on this set from a totality of 3 to 2. So player 2 now just plays another coloring, which is the restriction of C to this set, to which player 1 plays another infinite homogeneous set, and now you've eliminated yet another color from 2 to 1. Now it's actually homogeneous for C. The details of that are not so important. What's important is just to count how many moves this took, right? So this took 1, 2, 3 moves. Okay, this game took 3 moves. You can imagine that has something to do with this number here, and indeed it does, right? If player 1 had played instead a coloring from omega to 4, as it can, since it can play any instance of RT1 less than infinity at once, this game would have taken 4 moves, 5 moves, 6 moves, depending on the number of colors that player 1's initial coloring played. And in fact, Hirschfeld and Jocker showed that there is no n such that player 2 has a computable winning strategy for this game that wins in at most n moves. So there's no bound. There's no way to bound the number of moves for player 2's winning strategies here. Player 2 always wins, always has a winning strategy, but depending on the instance played by player 1 on the opening move, the game can take longer and longer and longer. And what sort of got Sarah and Dennis me interested in this was thinking exactly about this point, right? If you compare this with what's known in reverse math and sort of on the proof theory side, we know that RCA naught proves RT12, but RCA naught does not prove RT1 less than infinity. RT1 less than infinity, by an old result of Jeff Hurst, is equivalent to sigma 2 bounding, which is stronger than sigma 1 induction, and that's all RCA naught can prove as far as first order things. In some sense, we were led to ask, whether or not the fact that there is no bound here is somehow a reflection of this fact here, that RCA naught in particular does not prove that RT12 implies RT1 less than infinity, right? So this implication is not provable in RCA naught. It's true over omega models, but there's no bound. Okay. So this led us to generalize the Hirschfeld-Jacques game in 2 different ways. So the first way that here is actually, there's a variant of it also given by Hirschfeld and Jacques for RCA naught, but I'm going to state them here sort of together. So in our setup, we have the following. So let P and Q be problems, and gamma is a set of L2 formulas, just a set of formulas in second order arithmetic, language of second order arithmetic. The gamma game, I'm going to call this the gamma game, Q implies P, is the following. So it's very similar to the Hirschfeld-Jacques game, except now we're playing not over omega models necessarily. So what does player 1 play? It plays an L1 structure, M, and it plays an instance X naught of P, just like it did in the original game. It plays an instance of the original one. It has a little bit more constraint here. The constraint being that we want M together with, if we look at M with this as in its sort of second order part, that be consistent with gamma in the sense that there is an actual model of gamma, which is a second order fragment of second order arithmetic, that there's actually a model of gamma that contains this fragment. So having the same first order part as M and containing X naught. That's what I mean by consistent. Okay, so player 1 plays first order structure and an instance of P so that the 2 together can be extended to a model of gamma. Player 2 does what it did before. It plays something computable from X naught. Computable now in the sense of the model, right? So it should be in this structure right here, right? So by this I just mean the delta 0, the collection of sets delta 1 definable from X naught over subsets of M, delta 1 definable over X naught. And again, the conditions on what Y1 is exactly the same. Either it's a solution to X naught or it's a Q instance. What does player 1 respond with? It responds with a solution to player 2's instance. But it has a little bit more to do this time again. Now it needs to be that the collection of sets delta 1 definable from X naught and X1 is consistent with gamma, is extendable to a full model of gamma. Player 2 does exactly before, plays something quote unquote computable from X naught and X1, right? It's either a solution to the original X naught or it's a new Q instance. Okay. Player 1 on its third move responds by playing a solution to that as a problem of Q, subject to the fact that now MX0, X1, X2 is consistent with gamma, and so on. So this is the modified gamma game that Hirschfeld and Jacques did define this for gamma equal RCA naught. But I'm going to define one more variant that we considered, which is the following: that player 1 now has a slightly harder job. Player 1 has to actually not play just an instance of P and a first order structure M, so that M together with that instance is consistent with gamma. Player 1 just flat out has to play a model of gamma on its first move. So player 1 plays MS, which is a model of gamma, and an instance X naught that's in the second order part. Okay, and henceforth, player 1 is committed to playing entirely within S. All of its moves come from S. Player 2 plays exactly as before. It always plays, quote unquote, computably from player 1's moves. Okay, so whatever player 1 has played up to this point, player 2 can pick something that's delta 0, 1 definable from that. And again, the winning conditions on these games are exactly as they were in the initial game. If player 2 ever wins, plays a solution to the initial instance of player 1's the P instance X naught, player 2 wins. If player 1 can't respond for some reason, player 2 wins. And if otherwise, the game goes on forever, and then we say player 1. Okay, so we have the gamma game, G gamma, and then we have this modified gamma game. Okay, so this is what I'll call them. So if you know, it's one of these things where you don't. This may seem quite opaque, but if you sort of just think about it a little bit, you'll see that in sort of in order of difficulty, right? The gamma game is the hardest one for player 2 to win. There are fewest restrictions on player 1. The modified gamma game is the hardest for player 1 to win. In fact, even harder still is the gamma plus Q game. Where you might sort of say, well, if I'm proving Q implies P over gamma, then it doesn't matter whether I'm working over gamma plus Q or over gamma itself. But it does matter in some instances, and I'm mostly listing this here for completeness. I'm not going to dwell on this. But the modified games are harder for player 1 to win. The unmodified games are harder for player 2 to win. So what did we show? So these are the main results, and I'll be talking about these in the remainder of the talk. So suppose we have problems P and Q, and suppose we have gamma, which is a consistent extension of delta 0, 1 comprehension by pi 1, 1 formulas, e.g. RCA naught. If gamma proves that Q implies P, then player 2 has a winning strategy in the gamma game. If gamma does not prove Q implies P, then player 1 has a winning strategy in the modified gamma plus Q game. So if gamma proves Q implies P, then player 2 wins all of these games. Has a winning strategy in all of these games. If gamma does not prove Q implies P, then player 1 has a winning strategy in all of these games. Okay, so all of these, there's no distinction. But here's the kind of thing that motivated our looking into this, and that that was sort of the real payoff of this, and why we kind of fumbled for a long time for the right definition. So same exact setup. Gamma is a consistent extension of delta 1 comprehension by pi 1, 1 formulas, but now we include a universal sigma 0, 1 formula. So for example, RCA naught includes a universal sigma 0, 1 formula, and that's so this is just to facilitate some coding. If gamma proves that Q implies P, then there's an actual fixed n, so that player 2 has a winning strategy for the modified gamma game, Q implies P, that ensures victory in at most n moves. Otherwise, player 1 has a winning strategy for the modified gamma plus Q game. So again, for all of these, right? So the difference is, so now we're saying, not only does player 2 have a winning strategy, but the number of moves which are required is bounded by a number n that's independent of player 1's initial move, right? So the actual moves don't determine the length of the game. There's a bound, and it's fixed, right? The drawback is that, right, we only have this for this game. We do not know about these, and I'll return to that a little bit later on, and I'll say some things about that. Morally, right? If we think back to that example with RT1 less than infinity and RT1 2, we had a situation where RCA naught did not prove that RT1 2 implies RT1 less than infinity, and we had no bound. Here we're saying if we do have a proof, there is a bound, and kind of the idea and what sort of led us to think that this could be true is just that, okay, if you have a proof, proofs are finite, right? And if you're proving Q implies P, that proof's going to use Q finitely many times. You can only write it finitely many times on a page. And that would seem to make this almost trivial, right? Except that it isn't. I mean, it's actually quite subtle, because proofs can be complicated, right? I mean, this audience probably knows that better than anyone. But right, I mean, if you have a proof by contradiction, it's very difficult to measure in any sense how many times you actually used the antecedent or something like that, right? I mean, it becomes a lot less straightforward. The proof branches somehow, does cases, does some kind of iteration. I mean, things can be quite complicated. Nonetheless, we can get this intuitively this result that intuitively makes sense. And I'll sketch a proof of this in a couple slides. Let me give a couple applications of it first, though. So that I think are quite nice. So there's a nice folklore result, actually, that I think many of us, at least I know I did it, I know some others did, learned from Carl at various times. This is this. So if AC not proves some principle P, then there's an N so that every instance X of P has a solution computable in N jumps of X. So N is a fixed standard number, and every instance of X has a solution computable in X of N. ACA, right, you can think of ACA as RCA plus the statement for every X jump exists. The Turing jump of X exists. This is saying that if AC not proves P, the number of jumps can't be unbounded, right? Overall, the instances can't be unbounded. So here's how this. So this is there's a couple different ways to prove this. There's a model theoretic proof, but it's actually a fairly easy consequence of our main result, right? So so suppose that ACA naught proves P, then RCA naught proves Q implies P, where Q is for all X jump exists. Okay, so we know that if we look at this game, the modified RCA naught game, then player 2 has a winning strategy for this game because RCA naught proves Q implies P, and by our result, in fact, the number of moves bounded by the number of moves in which player 2 can always win is some N which is independent of the instances. So fix this N. And now consider the following run of the game. Player 1 on its first move plays an instance of the problem P, and it plays this omega model of RCA naught. This is an omega model. This is just a set of all sets that are computable in X to the N, the Nth jump of X. Every set that is played in the entirety of this game is going to be in this set. Therefore, it's going to be computable in X to the N. Since player 2 eventually wins this, it must play a solution, ergo there must be a solution that's computable in X to the N. Right, so it's a very simple application. Here's another one. So notice that if right, the generality of the theorem is that we take delta 1 comprehension and we expand it by pi 1 formulas. If those pi 1 formulas are actually true, right, then meaning true over the standard natural numbers, then player 1 can always play an omega model on its opening move. And therefore, right, if player 2 has a winning strategy for the modified gamma game, it also has to have a winning strategy for the original Hirschfeld-Jokic game that just works over omega model. So if we look at just here one sort of vignette, so this is Ramsey's theorem for pairs, 2 colors, and Ramsey's theorem for pairs in arbitrarily many colors. Pate showed that there's no bound on player 2's moves in this game, the original Hirschfeld-Jokic game, right? So this is a parallel result to that example I showed with RT1, 2 and RT1 less than infinity, although this uses different argument. And by what I just said, this means that RT22 does not prove RT2 less than infinity, even if you try to do that over RC naught plus all true pi 1 formulas. Which is, it's a sizable chunk, right? A sizable increase. And why that's even sort of kind of interesting given existing literature is that we know RT22 does not imply RT2 less than infinity over RCA naught. That's by a result of Cholak, Jokic, and Slayman. But the way their proof works is that it constructs a non-standard model, right? And in particular, a non-standard model in which some amount of arithmetical induction fails.
Sure. Actually, this result due to CTAPN, like this particular one, it appears in the paper. Due to CTAPN, right? He showed that.
Is actually, it could be. I don't know. I know it from this paper, but maybe Carl knows better.
I think that in this paper.
Is that in the CTAPN Slayman 95 paper? They actually had this result as well. It could be. So I caveat that then by yeah, it could be that this was already in the Cedap and Slanted paper. But in any case, the way it's separated is by so my apologies if I misattributed that. The separation is by a failure of some amount of arithmetical induction. Arithmetical induction is a true pi1-1 statement, right? So there's no hope of pushing that proof to also get this enhanced result, right? Because you can't. I mean, the argument doesn't work. Okay. So let me give an idea of how this proof goes. It's a nice proof, I think. It's not too complicated, even though it's a little maybe looks intimidating on this slide. But remember what the idea is, right? So the game is that player one is playing instances and solutions, an instance of P and solutions to instances of Q. Player one is sort of playing them arbitrarily. Player two has to play all of its moves computably from player one's moves, right? So here's a formula, theta n, for each n, let theta n be the following formula. Theta n holds of parameters which are numbers e0 through en, sets x0 through xn, and y0 through yn. Y0, yn don't need to be there. They're just there sort of to make things easier to state. But all we're saying is that what this formula says is if x0 is a P instance, so this could be an initial move played by player one, and y0 is computed from x0 via the functional with index e0, and y0 is a P solution to x0, or y0 is a Q instance, and if x1 is a Q solution to y0 and y1 is computed from x0 and x1 using e1, and y1 is either a P solution or it's another Q instance. So this is just saying, it's describing the situation, the run of the game, right? And it continues all the way to the end, at which point it says, and yn is a solution to the original instance x0, right? So it's saying this set is computable from this one via this number. The next set is computable from these first two sets via the second number, and so on, right? With the understanding that the very last set is an actual solution to the original instance. So theta n is saying there's a run. This is a run of the game, and it takes n moves. And now let's let delta n be the statement. Whatever player one plays as its first instance, there is something, there is a way to compute some next move of player two's from it, such that whatever player one plays on its next move, there is a way to compute, and so on, such that this formula holds. So delta n says, right? Delta n says player two has a winning strategy that takes n moves, that takes at most n moves. That's what delta n says. And so what we're trying to show is that if gamma proves Q implies P, then gamma proves delta n for some n in omega. That's the goal, right? So suppose gamma proves Q implies P, but gamma doesn't prove delta n for all n. If I just go back here real quick, right? So what does that mean? That means delta n fails. Oops. Delta n fails for every n. So all of these quantifiers flip, right? And so what we can do is we can replace. So we're saying there is an x0 such that for all e0, blah blah. There is an x1 such that for all e1 there is an etc. So what we can do is we can just take a Skolem function for this formula, right? We can take a function that from nothing gives us the initial witness to this quantifier when it's flipped to an existential. Then for every e0 on input e0, it gives us an appropriate witness to the next existential x1 and so on. That's Skolem function, right? And what we want to do is we want to do some kind of compactness argument. So here's me obliging Roman with remembering the title of my talk. Compactness is showing up, right? So we're going to add a function symbol that's going to represent this Skolem function into our language. So this is a function that goes from first order objects numbers to second order object sets. We're in second order arithmetic, so this is fine. We can declare a function symbol like this. So we've expanded our language, and now for each n, fix a model M of gamma in which not delta n is true, right? in this model, there is this Golem function from the previous slide, and that's how we interpret this new function symbol. Okay, so now let's just take a formula that represents the statement that f is interpreted as the Golem function, right? So psi says it's exactly just the negation of delta n, except all the existentials over the xn, over the xi's, x0, x1, are replaced by the values of f. Right? I mean, f is a Golem function for some existential statements, right? So that's exactly what it should do, or it's interpreted as a Golem function. So we have this formula here. M is a model. M over here is a model of that sentence. M is a model of this. Therefore, there's this sentence. You know, each one of these CNs is satisfiable for every n, together with gamma. Right? So by compactness, we can actually fix a model of, you know, it's satisfiable for gamma together with C1, C2, C3 for all n's is satisfiable, right? So we can fix a model n of gamma and all of these CNs, and now take the interpretation of this function f, right? So it's a simultaneous Golem function for all of the delta n's failing. That now tells us how to play how to do a run of the game, the G gamma game, in which player one wins, right? And that's not possible, because if you have a run of player one's game, if you have a run of this game in which player one wins, then gamma cannot prove that Q implies P, right? So since gamma proves Q implies P, this is impossible. So that's the argument, right? So it's really a nice kind of compactness argument that pulls it together. Okay, so I want to talk about just to wrap up here with sort of some extensions of this stuff, right? So so as I mentioned before, we don't know whether our result works if you look at the gamma game instead of the modified gamma game. So again, right, we don't know whether that number of moves being independent of the run of the game can be obtained in the actual full gamma game and not just the modified gamma game. But in natural cases where player two isn't sort of getting instructions from a divine source or something like that, if there's some nice definable down-to-earth strategy, then actually we can get this. This is the theorem. So let P and Q be problems, let gamma be a consistent extension of delta 1 comprehension by pi 1 formulas. I guess that should also say that it includes a universal sigma 1 formula. Then the following are equivalent. Player 2 has a computable winning strategy in the modified gamma game. Player 2 has a computable winning strategy in the unmodified gamma game. There's a number n that bounds the number of moves in the computable winning strategy of player 2 in the modified game. There's a number n that bounds the number of moves in which player 2 wins in the unmodified gamma game. And in fact, this bound is the same between these two 3 and 4, right? So long as you have a computable strategy, and in fact, it doesn't have to be computable, it could work for other complexity classes too, then in fact, we do have this bound, and it works the same in the modified or unmodified game. Okay, I want to give just real quick, Roman, can I have a couple more minutes, or am I out of time now?
No, sure, no, there is plenty of time.
Okay, oh, sorry, I didn't know how long we run. Okay, so good, so then I can do it. So, okay, so I want to talk about variations of B sigma 2. So I feel silly saying it here because probably everybody knows this, but let me just say it so this to be complete. So suppose we have a class gamma of L2 formulas, then B gamma is the bounding scheme for formulas in gamma, right? So this says, if every number smaller than n has a witness so that phi of xy holds, then there's a bound on so that each number smaller than n, we can find that witness below B. So this is a particular kind of first order statement, and a frequently encountered principle, a sort of example of this that in reverse math is B sigma 0 2, right? So oftentimes when you have some kind of priority argument or something like that, and you want to say that from some stage on something is true or something like that, you need to use B sigma 0 2, and it's something that shows up fairly often and is easy to kind of forget about a lot of times. But B sigma 2 is, I mean, why it's a problem is because it's not provable in RCA naught, right? So if you're using it to claim something's provable in RCA naught, you have a problem. It has a lot of important equivalent formulations, right? So I already mentioned this result of Jeff Hurst that B sigma 2 is equivalent to RT1 less than infinity. Now, if you're sort of thinking of, you know, these are equivalences over RCA naught, each of these equivalences corresponds to a winning strategy for player 2 in the modified gamma game over RCA naught, right? And an interesting question is, for which of these kinds of equivalences can we choose? Are there computable strategies? And we now have a way of answering that question quite easily, right? Without having to really get into complicated proof theory, because we have this connection between computable strategies and bounds on the length of the run, right? So one way we could, for example, try to show that there is no bound on the length of run of player 2's winning strategies in the modified game. One way we could show that there's no computable strategy is to show that there's no bound on the length of the run. So here's a concrete example. This is we call this LH for limit homogeneous. This is a very, very trivial problem. So suppose you have a coloring of pairs of integers with 2 colors. So each pair you color 0 or 1. But in fact, for each x, the color CXY is eventually equal to 1 for all sufficiently large y, right? So C of 0, 1 might be 0, C of 0, 2 might be 1, C of 0, 3 might be 0. Could alternate for a while, but eventually it's 1, 1, 1. C of 0, 17 is 1, C of 0, 18 is 1, and so on, right? So this is what we call a stable coloring of pairs in sort of the computable combinatorics world. But you know, it just has this simple thing that all of these colors eventually limit to 1. So what does LH say? It says there's an infinite set H so that CXY is equal to 1 for all x and y's. Okay, so how, you know, that's really simple, right? Because if everything is eventually colored 1 with everything, you just fix the first number, look far enough out, you'll find something that colors 1 with it, right? Now look far enough out, you'll find something that colors 1 with both of them. Look far enough out, you'll find something that colors 1 with everything, right? And so on. Okay, sorry, there's a comment. Oh, I'll read it. So that seems straightforward, but in fact, this principle is equivalent to B sigma 2. So, and it's instructive for what I want to say to look at the proof real quick. So let's prove that B sigma 2 implies this principle. Okay, then what do? Well, you have this recursive process that I just described. Like fix the first element, find something that colors 1 with it, find something that colors 1 with both of them, find something colors that 1 with all of these, right? All you have to prove is that this is actually, I mean, this is a recursive process. All you have to do is prove that it's actually total, right? That given finitely many things, you can find something sufficiently far out that colors 1 with all of these things before, right? Well, that's B sigma 2 will exactly tell, right? Because I mean, the issue is from the audience's perspective, right? You have, or maybe I'm mirrored. I don't really know, but okay. So you have a number, and you know that from some point on you color 1. Okay. You have another number. You know from some point on you color 1, right? But if you do this for finite in the sense of a non-standard model, that point might be the point at which they all color 1 with might actually be infinite, right? So it might not be a specific number. B sigma 2 unfortunately comes in and says, no, there's a bound, and all of these numbers up to this point are colored 1 with everything from now on. So B sigma 2 is only used in the verification, right? B sigma 2 is not used in any constructive fashion, in any computability theoretic sense. It's used purely proof theoretically to argue that you can't be 2 non-standard. What about in the other direction? LH implies, so let's prove that LH implies RT1 less than infinity. So here we actually get, again, nothing constructive. So let's pick a coloring that uses finitely many colors, but let's assume there's no homogeneous set that's infinite. So define an instance of LH as follows. C of xy is 0 if the color of x and y is the same under the instance of LH, under the instance of, right, so I'm defining a coloring of pairs, sorry. CXY is 0 if the color is the same, and CXY is 1 otherwise. You have to have every, that every color is eventually, every element is eventually colored 1 with everything, right? Because, I mean, you can't, otherwise you'd have an infinite homogeneous set right there. So the limit of CXY is equal to 1 for all x, as we need. It's an instance of LH, apply LH, and get a homogeneous set, right? So now you have a homogeneous set. Every pair of elements in it is colored different, right? So just pick k plus 1 many things, and now you have a contradiction to the fact that the D only uses k many colors, right? So again, it's not what we would say as any kind of like computability theoretic proof, right? We're not using LH to build anything. We're merely making some kind of proof theoretic argument. So that's an interesting aspect of this that is sort of confirmed by the next slide, which is that if you're looking at this example RT1 less than infinity implying LH, player 2 has no computable winning strategy for this game, and this is true even if the number of colors is right. When you're giving an instance of RT1 less than infinity, you can say, well, here's a coloring, and it's a coloring that uses k colors, and I'm telling you what the k is. Or you could say, here's a coloring, and it uses finitely many colors, but I'm not telling you about. It uses finitely many, but you have to guess at it, or something like that. So whether or not you do that doesn't affect this result. That's one issue where things could become kind of complicated with this stuff. So, but here it doesn't make any sense, any difference. Player 2 has no computable winning strategy for this game, and the way we can use it is by appealing to our results in terms of the length of the winning strategies, right? So here's just the idea of the proof. So player 1 begins by playing a standard model of the natural numbers, right? We're trying to show that this game is long, right? So we're going to play as player 1. So player 1 begins with playing a standard model of the natural numbers along with some initial segment of an instance of LH. So we're just coloring arbitrarily. Player 2 should be from this computing, as playing according to some computable strategy, needs to start building an instance of RT1 less than infinity. So some kind of finite coloring, right? Coloring that uses finitely many colors. Now we can guess at the number of colors that this player is going to use, right? Right, we can say, oh, you're only using 2 colors. We're going to do something. Player 2 can try to trick us and say, no, I'm only using 3 colors. And we can say, okay, well then we're going to change something. And then player 2 can say, oh no, I'm using 4 colors. That can only happen finitely often, right? I mean, the number of times that can go up before player 2 loses the game by not actually playing an instance of RT1 less than infinity is only finitely many times, right? So eventually player 2 has to settle on a number of colors. And at that point, we have the right guess. At that point, we're guessing that player 2's strategy is using the right number of guesses. We're in a standard model of RCA naught. Player 2's a standard model of the natural numbers, first order structure. Player 2's coloring is using k colors for some k. What we can do is now pass to a 1 elementary extension in which B sigma 2 fails. So actually we learned this from Roman's book that you can do this. So this 1 elementary extension is going to preserve the fact that player 2's coloring only uses k many colors. That's a 1 quantifier statement. But because it's a failure of B sigma 2, LH fails in there because LH and B sigma 2 are equivalent. So we can now take that instance of LH, which has no solution in this model, modify it a little bit on initial segment, and get an instance of LH in which with no solution. And now player 2 cannot win. In that model, player 2 cannot win, right? Player 2 can never play a solution to our instance of LH because player 2 has to stay inside this model. There is no solution, right? So that's a kind of superficial just idea of how the proof goes, but it gives the flavor. So this has a lot of applications like this of really teasing apart these very subtle principles, which are not, which really can't be told apart. I mean, certainly not from the point of view of provability alone, but also not from the point of view of any of these existing finer reductions, right? I mean, computable reducibility, Weierach reducibility, or anything like this. But we have framework that sort of refines them all, right? I mean, also kind of fits all these different reductions, but refines them, right? So here are just 2 slides to wrap up with. So this is a picture of a couple of different things, all of which are equivalent to B sigma 2 under Weierach reducibility. So Weierach reducibility does also have this feature that things that are equivalent provably tend to break apart, right, sometimes. So here we have RT1 less than infinity, here's LH. Here's this stronger form of RT1 less than infinity where the number of colors is not specified. And here are a variety of results that are from the computable analysis Weierach literature. So this is closed choice on the natural numbers, closed choice with finitely many errors, bound. These are principles that, for folks who know what they are. I should say all of these principles are provably equivalent and all of these principles are computably equivalent, right? Under Weierach reduction, we have some ability to tell them apart, and under our game framework, we have even more sort of splitting, right? So we have a much sort of broader kind of zoo of principles, and it's telling us something again about how these various principles relate to each other, right? In particular, the kind of moral of the vignette that I gave with respect to LH and R21 less than infinity is that this framework in some sense allows us to say quite precisely, or at least more precisely, right, when a proof between 2 principles is sort of purely computability theoretic or purely proof theoretic or something in between, right? So the fact that the game theoretic network is game theoretic framework is saying that these things are different is somehow saying that neither one is proof from the other in any kind of computability theoretic fashion. The fact that we're computing things from each other in there is not really what's going on, right? You're using them purely in this kind of ancillary verification way to check that a certain construction that exists anyway works out and has all the right properties. So I think that's an interesting kind of way to think of this and sort of a way in which it complements the existing approaches in this stuff. And that's it. So I'll stop right there. Thanks.
Thank you, Damir.
Thanks.
Time for questions.
I think I can. Okay. If I X out of that, then I see people more.
I have a question.
Yeah.
So maybe I'll try to show myself. Well, let's see. Okay. So there is in some of the other areas of logic, there are kind of similar games. In particular, in bounded arithmetic, there are student-teacher games that correspond to provability in a theory for polynomial time. This is known as the Kpt Witnessing Theorem. Even one of the proofs is kind of similar. It goes by this compactness argument. The original proof was by Hebron's theorem, I guess. But the question is, in that case, the witnessing theorem gives like a polynomial time finite round strategy for essentially any for all exists for all statement. So do you think this sort of game theoretic would work for general pi1 statements, or is it specifically for these implications between pi1 statements that you've been considering?
So how do you mean? I don't understand. I mean, so all of the problems I'm talking about are pi1 statements. Sorry, I guess I don't need to.
Yeah, but the implication is a pi1 statement essentially. Right?
Oh, I see. Yes,
right?
yes, that's right.
Do you think you'd have this sort of game corresponding to provability of pi1 statements in reasonable theories in general? Where one of the players would be basically coming up with the witnesses for the existential quantifier. The other player would be showing counterexamples, pointing out that this doesn't work, and eventually the player who witnesses the middle existential quantifier is expected to win, right? To come up with a witness that can be argued against. So, have you considered that at all?
Not like that. I mean, that's very interesting that we hadn't thought of that. We did think about implication. I mean, a game theoretic framework that could capture implications between things other than pi1 statements, for example, pi1 statements. but again, implications between them, right? So that you could sort of say, well,
Yeah,
what
that goes a
should be-
little bit beyond that. I mean,
right. So this is a little different.
Mhm. Yeah, right.
Other than as, I mean, sort of, you know, as some kind of way of cheating. I mean, in the sense that if you come up with a way of a game theoretic framework for, say, implications between pi1-3 statements, which is something we do have some candidates for, but it becomes quite difficult because now you're talking about principles that aren't necessarily absolute between omega models, and so things become very difficult. Then maybe you could cheat somehow, right? I mean, you could have some kind of like verum or something like that, and use that as an implication between the principle you're trying to prove, or something like that, and fold what you're saying into that. But we haven't thought of that explicitly, whether this more general kind of sense of pi1, and that's very interesting. I mean, it could be, and like you say, these things all share I guess they share the same kind of approach of the proof, right? I mean, like Wang's this result that we know from Wang about ACA, if it proves a result and it's computable in some number of jumps, it also has exactly the same shape. I mean, it doesn't have the Skolem function, all this that was specific here, but it has roughly the same compactness. So it could be that something like that could work more generally, indeed.
Thanks.
Yeah, no, that's really interesting. I'm gonna think about that.
Yeah, I have a question.
Sure.
These various games, they look sort of complicated. You're playing entire sets and things, just go back and forth. But they're all determined.
Yes.
Determined games. Now, are they all instances of open games in some big space somewhere, or is it all game by game that you determine that they are determined?
I mean, they should be. Yeah, they should be. Right. They should all be open games, I guess. No. I haven't thought about the complexity of this, but I mean, it's something very low level that shouldn't. Yeah, it shouldn't go anywhere near where things get interesting for determinists or anything like that. They're anyway. What I'll say is that it's very easy to see that they're determined. It doesnes even require thinking about open games or anything like that. So.
My second
but
question.
I just haven't thought about it in a while.
Okay.
To give you immediately
My second question is, what happened to Hao Wang?
What happened to
Hao Wang?
Oh, is this the name of the person to whom this theorem?
No, you in the slide. I'm sorry, in the abstract I read, you said that this gave a new a generalization of a proof theoretic principle due to Hao Wang.
So maybe I miswrote that in the other. So it's in either a paper. I think it's a paper by Hao Wang. But it is in fact he who says that it is a folklore result. So I should have said maybe
okay.
that
okay.
when I wrote folklore here,
Okay.
According to H. Wang, but
how? Okay,
yeah. So I don't know at all the history of who initially proved this. I mean, it could very well be that it was Hao Wang who proved it and just sort of thought, oh, everybody knows this, so it's folklore. Yeah.
Thank you.
But yeah, I should have mentioned that. Thanks. Yeah.
Oh, actually, one other thing. In one of the middle slides, you had Y1, Y1, Y1. And I think the last Y1 should have been a Y2.
Oh gosh, that could very well be. Yeah, I'm not on my index game today, unfortunately. Okay, I'll scour through that and find it. Thanks. Sorry for all those.
Can I add one more note about Hao Wang?
Yes, please.
So the first time I saw this result, Wang has a book called Popular Lectures in Mathematical Logic.
I think this is where this result is known. We know this result from.
Right. And the interesting thing is that he credits Carl Jokers and Solovey, and I had some correspondence with Carl about 9 years ago, and he didn't exactly recall having such a correspondence. So there seems to be some sort of a loop where basically Wang points to Jokers and Jokers points to Wang. So
Okay, I see. Okay. So yeah, maybe we can ask Carl next time we talk or something. It's be good to try. I mean, it's now coming up as an example in a lot of papers, and so maybe it'd be worth tracking down the exact history of this if it's at all possible.
Carl is in the audience, by the way.
Say that again, Stefan?
Carl is in the audience.
Is he still in the? He is in the audience. Yeah. Hi, Carl. Carl, did you prove this result by yourself? Maybe he stepped away, but he did actually. Carl told me that he might have to run, so it may be that he has already left. But he pointed out in the chat, and I can't access it for some reason now, but that it was from the CJS paper, right? The RT22 and RT2 less than infinity. So
that was Bartosz.
Oh, it was Bartosz. Okay, sorry. Thanks. Yeah, I didn't. Oh, now I have the chat. Okay, great. Yeah, thanks.
Can I ask a question?
Yeah.
There's a couple places. There's really only one place where you actually point out significance of an actual n in these proofs, right? That sort of if n is equal, if it's a computable reduction, or if one problem is computable, it's computably reducible to other, then n is equal to 2 in
right.
in this thing. And is there any other significance to any other n that is besides just finite versus infinite?
Well, we don't. I mean, not like to my knowledge, not like a general. Like it's
Like, is there some kind of hierarchy there?
Yeah, like a well-known reduction corresponds to n equals 6 of this or something like this. I don't know of anything like that. But I mean, there are examples where different n's show up for specific theorems. Like, I mean, if you're trying to show that, RTN 17 implies RTN2 implies RTN 17, that's going to have an n that's natural and specific to those numbers, right? Maybe that's, I assume that's not actually what you mean, but yeah. So I'm not sure if any other kind of reducibilities always work with any other ends or not. And things get a little complicated around n equal 1. So if you're, right, because of the way these things work, so if you have something like a computably true principle where you just have an instance, and every instance computes a solution to itself. So you think, well, that's a really silly principle. Right? I mean, from the computability theory principle side, right? It's trivial. It should be n reducible to everything, right? I mean, but it may not be computably reducible to anything, right? For example, if it has an instance that's very complex, let's say a computable instance, it's not going to be reducible to a principle that has no computable instance, right? Because it can't compute the instance, you can't even get the reduction off the ground. You can't even translate from the one problem to the other, let alone to do something on the solutions. So you could have these situations where you have a computably true principle and it's computably true, but it's not actually computably reducible to another principle, right? Whereas this framework sort of captures the n equal 1 case, will allow for that to happen. You could have that P is reducible to Q via 1, where player 2 wins always in one move, but that does not imply computable reduction. So computable reduction is exactly n equal 2, which is somewhat strange. Maybe it's not less than or equal to 2, as maybe one would want.
No more questions?
I just wanted to say hi, Jim. Nice to see you.
Hello. Well, maybe he's not there. Is he?
He's there.
Hi, Damir. I enjoyed it.
Thanks. Yeah, it's good to see you. Are you in Arizona?
I am.
Nice.
Yep. Enjoying the nice weather here.
Right. Well, look at Russell is. Look how nice it is in these parts too.
It's not bad.
Yeah. Well.
All right. Look. So, I just want to remind you that next week we also have a session at 2, and from Warsaw, and Mateusz Wełych will speak. It's the second part of his talk, but it will be somewhat self-contained. So even if you haven't heard the first one, you might be interested. So Warwick next week.